Hello everyone. Myself Pradeep Kumar Vai, Assistant Professor, Department of ECE, ATMA College of Engineering, Mysuru. So in this video, let us look into an experiment called Full Adder, which is a part of HDL lab. So let us try to understand the Verilog code for Full Adder. And also let us look into the test bench to test the functionality of the design block. And very importantly, the main objective of this experiment is to understand the instantiation process. Instantiation means calling or invoking the lower level module in the higher level block or in the main module, so that by calling the lower level module, we can break down the larger design into a smaller blocks, and so that which makes easy in developing process. Okay, so that instantiation process we'll try to understand through this video with an experiment called full ladder. So this is the information regarding the full ladder block. We all know that full ladder is a combinational logic circuit which consists of three inputs and two outputs. The function of the full adder which adds two 1-bit number along with previously generated carry. Okay, or in total which can add three 1-bit number. So out of these three input, two are the 1-bit data and one carry in bit is the carry in or the carry generated from the previous bit. Okay, and which consists of two outputs, sum and carry out. The truth table for full adder is shown here. In case of full adder, if any of the uh, one input is 1 out of 3, if any one input is 1, then the sum will be 1. Or else if all the three inputs are 1, then also sum will be 1. Or else if any two inputs are 1, in this case 1 plus 1, which leads sum 0 with generation of the carry. Whereas in the last combination 1 plus 1 plus 1, 1 plus 1 sum is 0, which leads generates the or propagates the carry to the next stage, and that 0 plus 1 leads sum is equals to 1. Okay, this is the functionality of the full adder. So, or other the way, the full adder can also be expressed in terms of Boolean expression. If we reduce this truth table, so we will get an expression sum equals A XOR B XOR C, and C out or carry out is equals to AB plus BC in plus AC in. Okay, this is the Boolean expression for full adder. Now we will try to develop the Verilog code using data flow statement. Then in the next stage, we will understand how to develop the full adder code by using two half adder. Okay. Assuming that I have an information about the full adder in terms of Boolean expression, so I'll be dealing with data flow statement. So data flow statement, as described in the earlier video, is one of a low level abstraction of Verilog description, where the statements are in terms of Boolean expression, or we are going to show the relation between input output in terms of Boolean expression. Very firstly, we will declare the module with a keyword called module. The name of the module is full underscore adder, followed by within the parentheses list all the ports which are corresponds to the design or which is corresponds to the block. So in this particular full adder block, we have in total 5 ports which are listed as sum, C out, A, B, and C in. All the ports must be separated by comma, and the order in which you list the port doesn't matter here until unless if you are trying to establish the connection through ordered list. And the module declaration should be end with semicolon. The next statement is we will specify the direction of these ports. In this block, someone carry out are the output ports or output direction, which is specified through keyword called output sum comma C out. If the port are of similar nature, which can be listed in the same line. If they are in different, for example, the bit size of the ports are different. If sum is 1 bit, sorry, 2 bit, carry out is 1 bit. In that context, it has to be separated in the different line. So inputs, there are three input which can be declared through a keyword called input, followed by A, comma B, comma C. So this is the declaration of inputs and outputs. Straight away, we will establishing the relation between the input and output through data flow statement. So data flow statement, uh, should be specified through a keyword called assign. Assign is the keyword which assigns the calculated part of the RHS to the LHS. Okay. Here the sum is equals to A XOR B XOR C. So the logical operator XOR is cap. Cap is the XOR operator in Verilog. So therefore the sum is equals to A logical XOR with B XOR with C. So this calculated result will be assigned to sum. Similarly, the carry out is equals to A and B, or with B and C in, or with A and C in, say sum of product terms. Therefore, first we have to perform A and B. Therefore, logical and operation is ampersand. So A and B, this product term is ORed with B and C in, and this product term is ORed with A and C in, and it is end with semicolon. Okay, so this is a the straight away we are just trying to transform this Boolean expression in the assignment statement, so which completes the body of the full adder Verilog module. At last we can close, or we can complete this program our Verilog code with a keyword called end module. Okay, end module should not be in with semicolon. So this is the piece of Verilog code for full adder. Now we look into the test bench to simulate this full adder. Test bench is nothing but it is the uh, stimulus block which provides the necessary input signals and also which records the output. So let us consider the stimulus block as a main block, or it is a top level block to which I will instantiate the full adder model, and I will make an interconnection between the stimulus block and the full adder block, and I will generate the necessary signals, a combination of the inputs for full adder, and I will check the response of the full adder. Okay. The very first statement of the test bench is declaration of the module. So I declared a stimulus block with a name called as main, and which should not consist any ports. Since stimulus block is not synthesizable, which should not be declared with any ports. Okay, which doesn't consist any ports. And since my full adder consists of three inputs and two output, so all the signals which are intended to connect for the output should be declared as wire type, and all the signals variables which are intended to connect to the input should be declared as register type. Okay, therefore I declared S and C out, which are supposed to be connected to sum and carry out. So I'll declare this as S and C out. These two are the wire type. Likewise, I need to connect variable for A, B, and carry in from the stimulus block. So therefore, I declare a small a, small b, and small c in. These are all the variables which are declared as a register type and which are intended to connect for the input A, B, and carry in of the stimulus block. Okay, this is very important stage in the uh, test bench writing process. Okay, and then very essential that you have to instantiate, or you have to invoke the design block in the main module. So the design block should be invoked through its module name. So the module name of the full adder is written in the previous slide, that full underscore adder, which is invoked through its module name. Followed by we can specify the instance name. Let me call instance name as FA. Instance name is user defined name. Other than keyword, any instance name can be given here. And this is the statement to establish the interconnection between uh, okay. This is a statement which is to establish the interconnection between the stimulus block and the full adder block. So dot A, this is a port pin of the full adder which is connected to a variable A, that is register A. Okay, and the next connection should be separated by comma. Then I need to connect B. The B is the port, input port of the full adder. Therefore, I have to specify dot B is nothing but this is the port of the full adder. I am connecting to the small b, which is the register of the test bench. The next connection is separated by comma. Then dot C in, which is the carry in of full adder is connected to small cin, which is the variable in the stimulus block. Likewise, the sum and carry out of full adders are also connected to S and C out of stimulus block. So this is the connection by the name. This is the method referred as connection by name, where if you have more number of pins, which is obvious method, so where the order of the connection doesn't matter, but you have to specify both the instance port name as well as the stimulus block variable's name while establishing the connection. Okay, that instance, as long as the port rules are matched, this will be holds good. Okay, and next, let me initiate some control signals, so which can drive the values for the full adder or the design block. So that is kept in the initial statement. Initial statement is encapsulated between begin and end. So for ABC in 3 bit, there might be 8 combinations will exist. So only out of 8, I took 4 samples of combination. So initially I made A equals to 0, B equals to 0, and C in equals to 0. After 10 time units of delay, I changed the combinations of ABC as 0, 1, 1. And after 10 times of delay, 10 time units of delay, I changed the combination of ABC as 1, 1, 0. And after 10 time units of previous execution of the statement, have changed the combination as A equals 1, B equals 1, and C in equals 1. Okay, this is the if you want, you can even club some more combinations. You can exercise with that. Okay, now, very importantly, after interacting with the test bench with the full adder block, the result has to be displayed. To display the result, we popularly use a monitor system task statement. So, dollar monitor, this is a statement which monitors the variables which are listed within the parenthesis. If any changes happen in the variables listed in the parenthesis, the monitor statement will execute. So, dollar time will print the current simulation time, and whatever the statement which is encapsulated or enclosed within double quotes, those are all referred as a printable statements. So I am printing A equals, B equals, C in equals with triple three dashes and sum equals and C out equals. All the values are displayed in binary format, so that's percentage B. And after closing double quotes, that is printable statement, separate by comma, and mention the stimulus block variables, okay, which corresponds to that signal. So where A corresponds to small a, B corresponds to small b, C in corresponds to C in, S sum corresponds to S, and C out corresponds to C out. Therefore, the values which are acquired for these variables in the stimulus block will be displayed in accordance. Okay. At last, the test bench can be end with a keyword called endmon. So you can execute this in the online simulator tool, online Verilog simulator compiler. So this will be the response, expected response from the out of simulation. You can expect this response. At zeroth simulation time, the value of A, B, okay, fine. So I have copied both the test bench and as well as the full adder data flow statement to the online Verilog compiler simulation tool. Uh, this is the full adder block explained in the slide, and this is the test bench. Okay, let me simulate this. This is the test bench code showing for some combination. Let me execute this. So the simulation result is in the right side. But here at zero simulation time, the value of A is 0, B is 0, C in 0. Therefore, sum also 0 and C out also 0. At 10th simulation time, I have changed the value as 0, 1, 1, that is 0, 1, 1. In response to this combination of input, the output sum is 0, whereas C out is 1, that is 1 plus 1 leads to 0 by generating 1 bit carry. And the next combination after 10 time units of delay, at 20th time, okay, 20th time unit, the value of A is 1, B is 1, and C in is 0. which also leads to sum 0 and C out 0, that is C out 1. And at 30th time unit, since the last combination I have provided is 1, 1, 1, in response to that, sum is 1 and C out is 1. Or else, if you want some more combinations, you can include here. Okay. For example, I have included A equals 0, B equals 0, and C n equals 0. Then 0, 1, 1, 1, 1, 0. Let me include Ashton. Because after 10 time units of delay of previous execution, I'll change A value equals 1 and B value equals 0 and C in value equals 0. For this combination, the expected result is at 30th time unit, I supposed to get the sum as 1 and C out 0. And at 40th time unit, I'll get the last combination. Let me execute the same. Yes, at 30th unit, I have provided the combination A equals 1, B equals 0, and C in equals 0. Therefore, sum is 1 and C out equals to 0. So, therefore, by looking into the simulation result, you can conclude whether the designed module is functioning properly or